So this quiz was actually not meant to be awfully hard. I could have given a harder one. I could have asked you for a resistor as well. All right. So what have we learned is the relationship between the natural frequency and the inductor and capacitor. Apparently nothing. Awesome. That's 3 lectures down the crapper. Okay. So if you know the natural frequency, you know 1 over root LC. Can you get the natural frequency from this? Sure, right? You just count periods. So this looks like there's, let's see, that's 1 period. That's 2 periods. 2.5 periods. 2.5 periods in half a millisecond. Okay? So if 2.5 periods is half a millisecond, you can solve for 1 period is whatever, half divided by 2.5. So let's see. The frequency is therefore, right, the frequency is 2.5 cycles in 5 milliseconds is 5,000 hertz. Convert it to radians per second, you get that. Once you know your answer, once you know your frequency in radians per second, you can just solve for LC. You got to pick one or the other out of a hat, right? I mean, you have 2 unknowns in one equation, so you just pick one of them. You just say, okay, I'm going to have a 1 microfarad cap or whatever. You pick some number, you solve for the matching inductor. Done.
How do you get 2.5T, 12.5T?
Because I measured, I counted, right? I've got to count the period of this thing, right? So what's the period?
Wouldn't it peak from peak to peak and be like...
Fine, peak to peak. Good luck. You going to measure that? You can, if you could measure it, that's fine.
It's half of that.
Half of what?
No, so it would be from 0 to the 10.
Look, you can either do from here to here. Okay, that's fine. But there's no hash mark there, right? I mean, what is that number? It's a little less than halfway. So instead of guessing, I just say, look, that's 1, that's 2, that's 2.5. Took exactly half a millisecond. But you can guess if you want. I'll take a guess. If you looked at this and said 0.2, that's fine. I can live with that. If I give this quiz again on Wednesday, which I'm not going to, but if you wanted to get the resistance, if you wanted to get a matching resistor, what would you do? Right, you'd have to figure out roughly what the time constant is and solve for tau. Yes. Sounds good. We haven't solved that method. That's fine. That's fine. Right, what is the time constant? Do we need to do a lot of exponentials to figure out the time constant? 3 what? Time constant is 3 milliseconds? No.
63% of the total of the highest voltage.
You could do it that way. But if I just want to get a quick and dirty, divide by 5. 5 time constants is going to take roughly either, remember it has to settle completely within 5 time constants. So you could say 5 constants is 2.5 milliseconds or 3 milliseconds. I could take any of those, okay? So you could say 5 tau equals 2, 2.5, 3. That's your quick and dirty. That would give you a time constant. Once you know a time constant and you know your capacitance, you can solve for your resistor. Or if you want to get a bit more specific, you could look to see how long it takes to decay like 63%, maybe starting from initial value of 2. You could figure it out. That would be a little bit more accurate. In lab this week, this is exactly what you're doing, right? Have you guys read your pre-lab this week? Yes? Good, great, awesome. Well, in lab this week, we're showing you the plot, and we're saying pick resistors, capacitors, and inductors that will give you that step response. Right? So in lab, you're basically doing this quiz. except we changed the circuit around a little bit, right? Instead of having series, it's like partially series, partially parallel. So you have to derive a new transfer function. But that's the name of the game, right? If I show you this and I say pick RLs and Cs that give you that, you should be able to get something pretty close. All right, maybe you're off a little bit. You go and you say, oh, my resistor is a bit big. Maybe I should just make it a bit smaller or bigger or something. But you know, you should be able to get pretty close without too much drama. What do you think? Good. I'll pretend like everybody understands that.
Yeah, I use the same equation, but my numbers is off. Like, so my result.
Try changing the batteries on your calculator or something. I don't know. I don't know. We'll give you whatever points we can. Okay. Sine waves. You ready? We started this, didn't we, on Friday? A little bit. We started the sine wave conversation. Sine waves are fun. Okay. So let's see what we got. Will somebody tell me how to write a cosine expression for this cosine? I can't draw cosines too well. You have to pretend it's actually a real cosine. Here on out, for the rest of the semester, it's all cosines all the time. So we might as well spend some time making sure we all know what a cosine is. What's that? Is it seconds? Sure. Do you want to make it seconds? Or should we be dangerous and make it milliseconds? It's really not going to make much difference. Let's make it seconds. All right. Here. Ooh, I know. I'll start. I'll do the hard part. Let's write down, sort of. Let's write down the relevant number. What are the important numbers that we need to deal with? The magnitude. Okay, I need three numbers altogether. The magnitude, the frequency, and the shift or the phase. Okay, which is easiest to get to eyeball? Magnitude. What's my magnitude? 3. That goes out front. Because a regular cosine has a magnitude of 1. If you triple it, magnitude of 3. Sweet. Let's do frequency next. 0.476? Talking about where 0.476 came from. 1 over 2.1? 1 over 2.1. I'm not going there. How do we get the frequency of this thing? What is the period of it, first of all? Uh, 2.1 is the period? No? Okay, so here's me sort of being intentionally trying to draw attention to this. So let's say we start at this point. How long does it take before we get back to the same point? If I go, so here's 0.4 seconds. Okay, now it took me 2.5 seconds. See how that's exactly the same point on the cycle? So it didn't take me 2.1 seconds. It took me a full 2.5 seconds. You see the difference? Right. 2.4 seconds, 2.1 seconds is the time from here to here. But that's not a complete cycle. That's shorter than a complete cycle. So my complete cycle is, so we said the magnitude was 3. we said our complete period is 2.5 seconds. Now what? Frequency is 1 over t. I'm down with that. So let's see. What is 1 over 2.5? What's that? Is it really? Ha! Okay. That was just by accident. Okay. So what do I do with that number? Hit it with 2 pi. Omega 2 pi f. So that's 0.8 pi radians per second. And that's the number that goes in here. It's always the frequency in radians per second. So how about I do this? I say 2 pi times 0.4 t. Can that work? So this is this whole thing here. That's my frequency in radians per second. All right. How am I doing? So far, so good? Am I done?
Yeah.
No, I am not. Need to shift it. So how do I deal with a shift? Subtract or add a 0.4?
I think you subtract 0.4 because it's on the right side.
Like this? It's close. It's close, but it's not quite right. Yes. Yes, or radians now because you're an engineer. Right. Quick sanity check to know that I'm not quite where I need to be. What is the units of this frequency? Radians per second. If I multiply radians per second by seconds, I get radians. So this term here is radians. This term here is seconds. I cannot subtract two things of different units, right? It just, it doesn't work. So if this is radians, this better be radians. So I can fix this in one of two ways, and both are easy. One is I can do like that. Right? This is seconds. This is seconds. That's legitimate. I can do that. Yes?
Where's the spatial part?
The 0.4? Read it right off the picture. There's the 0.4, the shift to the right of 0.4 seconds. So I can do that, right? We know from, I don't know, whatever class they teach it in, if you take f of t minus some constant, that takes your signal and shifts it to the right by t units, right? And that's exactly what I'm doing here. The other option is just to convert it into a phase shift in terms of radians. So the other way I could say it is I could basically just distribute and say 3 cosine 2 pi 0.4 t minus, and then just multiply through. So if I do that, I'll get 2 pi times, let's see, what's 0.4 times 0.4? Is it 1.6? 0.16. 0.16. Okay, and that's a phase shift in radians. So that's phase shift in terms of radians. And if you do it like this is a time shift in terms of seconds. What does it mean? Is that a big shift? 2 pi times 0.016? How many radians in a full cycle? In a full period? Right. So one period equals 2 pi radians. How many radians am I shifting it in this problem? 2 pi times 0.16. So how many cycles am I, how many periods have I shifted it to the right? About 16%, right? So it's 0.16 of 1 period. Right? So just 16% of a period shift to the right. That's what the phase shift tells you. So you can either calculate your shift in terms of time or you can calculate your shift in terms of phase. If you shift it in terms of phase, that's exactly what that tells you. This number divided by 2 pi tells you the number, like the fraction of a period it's being shifted.
So why did you square find 4?
Because I just distributed, right? I took this number times this times t, that gave me that term, and then this number times 0.4, right? So 0.4 times 0.4, that's your 0.4 squared. That's why I wasn't thrilled that I picked that for my number, but it just worked out that way. Okay? So generally speaking, our generic cosine can be written like this. We have a constant k times cosine of omega t plus a phase angle theta all right, so k tells us how big, omega tells us how fast, that's the frequency, and theta tells us the phase shift, right? And in interpreting the phase shift, we can either think of it in one of like a couple ways, like we've just been doing. So we can either think of it, if we leave it in terms of radians, if we take theta and divide it by 2 pi, that tells us the fraction of a period. That tells us our shift in terms of fractions of a period. So if my theta was pi over 4, if my theta was pi over 4, how many periods am I shifting my signal to the right? Right, if I come to you, let's work this problem backwards. I started with a graph and I gave you you came up with the equation. Now I'll give you an equation, you'll come up with a graph. 2 cosine 6 pi t minus pi over 4. What am I drawing? Magnitude is 2, so let's start with that. That's pretty easy. How about my period next? Frequency is? Frequency in rads. Frequency in radians, 6 pi. Frequency in hertz, 3. Take that number divided by 2 pi. That gives me 3. And therefore my period is 1/3 of a second. Nice round number, Obaid. Awesome. Okay, we'll make do with it. Okay, so that's a shift of 1/3 of a second. Okay, now, sorry, that's a period of 1/3 of a second. What am I going to do with that pi over 4 nonsense? What's that going to do for me? It's a shift to the right. How much of a shift to the right? Right, so I have two choices. I can either say, and they both tell me the same thing. I can say, look, if one period gives me 2 pi radians per second, sorry, if one period gives me 2 pi radians, now I'm talking about a phase shift of pi over 4. How many periods is it? Can I cross multiply? Pi over 4 times 1 divided by 2 pi. That's what I was trying to say over here. So if I do that, what's that going to work out to? 1/8 of a period. So I'm going to take my cosine and shift it to the right by 1/8 of a period. So let's see here. If this is a whole period, there's a half a period, there's a quarter period, and there's 1/8 of a period. So, rats. Let's see, half. Helferty is so loud. How am I supposed to teach over that? Pretend that's sort of a cosine, right? It's a little gimpy, but we'll make do. Is that a cosine? Yep. Did I shift it to the right by 1/8 of a period? Pretty close. Okay. What's the time from here to here? That's a full period, right? 1/3 of a second. What's this time? What is this time that I've shifted it by? It's 1/8 of a third, right? Because it's an eighth of a cycle, and each cycle is a third. So this time here has to be 1/8 of a third of a second. So it's a 24th of a second. Slam dunk. All right, so the other way you could, to make your point, the other way you could interpret this is if you were to take it, if you were to factor out an omega from both terms, what would that leave you with? K cosine of omega, it would be t plus theta over omega. And if you did that, theta over omega would be your time shift in seconds. And that's exactly what Mike just told us. So you have two choices. You can either do time shift in terms of fractions of a period, right? In this case, we figured it was 1/8 of a period. Or if you do theta divided by omega, you can get your time shift in terms of seconds. So in our case, theta was pi over 4. Omega was 6 pi. That left us with 1/24th of a second. Okay, and that's exactly the time shift that we calculated. 1/8 times a third is a 24th of a second shift. There. It's exciting, isn't it, right? Don't worry. It gets better. We just got to lay the groundwork so that we can get to the exciting stuff. We actually know this stuff. Is this okay? If I give you a quiz on this on Wednesday, would you get it?
No. Yes.
Well, you have till Wednesday. How about that? I reserve the right to quiz you on this on Wednesday. Only because it's like cosines, right? This shouldn't be the first time you've seen cosines. Right? All we're doing is we're shifting them. Yeah?
So you said that from this point out we're always going to use cosines? So
For the most part.
So even if this was shifted so far, right, that it was basically a sine wave?
Yeah. A sine wave is just a cosine by another name. Right? It's a sine wave is just a cosine with a phase shift of 90 degrees. So we're going to use, we just use, yeah. Like when you see a sine, I want you to think of it as a cosine with a little phase shift on it. It's a good question. Yes?
I missed it, but how did you get the 1/8 for the 1/3 out of 1/3? Like 1/8?
Yeah. Okay, let's do that again because I want to make sure everybody gets that. This is sort of one of those little things for me that I really like everyone to get. So can we agree the phase shift was pi over 4 radians? Because that's written right on the, I mean, it's written there, right? The phase shift is pi over 4 radians. So it's pi over 4 to the right. But it's hard to look at pi over 4 and know what that means, right? Because it's not in units of seconds. It's hard to know just like intuitively what that means. We got to convert it into something that's a little bit more meaningful. And what I'm saying is we can do one of two things. One thing is we can convert it into fraction of a period. All right, so what I'm going to say is, so that calculation says, look, if 2 pi radians is 1 period, which it always is by definition, if 2 pi radians is 1 period, then how many periods is pi over 4 radians? Right? So it's just, I just cross multiply. You know, it's just scales. So in order to do that, I do pi over 4 times 1 divided by 2 pi, and that gave me 1/8 of a period. So I'm going to, so what this is telling me is I'm actually going to shift my cosine to the right by 1/8 of a period. So that's where the 1/8 came from. How long is 1/8 of a period? Well, 1 period is that long, a third. So 1/8 of a period had better be 1/8 of a period, a third. Okay. So that was one way of doing it. The other way of doing it was to look at our definition of cosine and say, look, if I factor out an omega from both terms, I'm left with cosine of omega times the quantity t plus theta over omega. Right? And you can tell that's right because if I distributed my omega back in there, I would get omega t plus omega times theta over omega. The omegas cancel, and you just get your theta back. So I know this is a correct factoring. Now if I do this, now my time shift, now theta over omega is a time shift in terms of seconds. And I know that because it's directly subtracting the t. So by doing that, I get a time shift in terms of seconds. So if I were to do that, in this case, so my time shift in terms of seconds is going to be theta over omega, which in this case is pi over 4 is my theta. My omega is 6 pi. And if I do that, I get 1/24 of a second, which, of course, is totally the same answer we got when we did 1/8 of a third. Has to be the same answer, right? There's only one right answer for how much you shift this thing by. So all we're having a conversation about is we started with a phase shift that didn't really mean much, and I had to do something so that I knew what it meant. One option was to convert it into a fraction of a period, which is a little bit more meaningful. The other option was to convert it into seconds, right? But it's all the same thing. And that way I know how to plot it. So come Wednesday, I should be able to give you a plot, and you can write the cosine expression, or I should be able to give you the cosine expression, you give me the plot, without using your calculator to like plot it and then just copy the plot off your calculator. Because that's kind of, well, you could do better.
We can do that for verifying.
You can do it for verifying purposes. Right? I like that. Okay. So how do we feel about this? We good? Okay, let's make it worse. Yes?
Does that show 1 cycle in 3 seconds or 3 cycles in 1 second?
This shows 3 in 1 second. There are 3 cycles, right? Because 1 cycle took 1/3 of a second. So if I do 3 of them, then I've done 3 cycles. You go. Okay. Okay. Can I make it worse? Here's the deal. Cosines are hard to work with because we're going to be taking a lot of derivatives and a lot of integrals. And cosines have this problem that when you take their derivative, they turn into sines. And when you integrate them, they turn into sines. And they just, okay, they're unseemly. So for a variety of reasons, we're going to employ a trick that on its face seems like it's going to make everybody's life harder. But I promise it's going to make everyone's life easier once you wrap your head around the math. Yes?
Can you just like treat it cosine like cosine before? It's like for 50 times like cosine, but 9 degrees off.
Yeah, but still, the math remains unwieldy if you do that. So here's what we're going to do. You may or may not have heard of the following expression. So is everybody cool with complex numbers?
I'm sorry, I'm still...
No, go.
time shift, we had theta over omega, and then the final is 1/24 of a second.
Yeah.
Can I just transfer the omega over 24 seconds is equal to theta? I mean, I'm sorry. Yeah. You got theta over omega, and then the final answer is 1/24.
Correct.
So I take that omega, put it over the 24.
Yeah.
Omega over 24 seconds is equal to theta.
For this problem,
Okay.
right, for this cosine, but for another cosine with a different frequency, it wouldn't work. So I don't know what that would tell you, but yeah.
Yeah, that's what I'm wondering. What was it telling?
Nothing.
Nothing?
No.
All right.
Okay. So we're all cool with complex numbers? We reviewed complex numbers, didn't we? Or was that my other class? I teach a lot of people. Okay. So I'm going to assume that everybody remembers complex numbers at some point. But just to remind you, a complex number has a real part and an imaginary part. Okay? Everybody know what J is? That's square root of -1. In the math department, they call it I. Over here, we need I for current. Okay, so we use J. Is this polar form or rectangular form? Rectangular form, right? What that means is, if you were to plot this complex number on a scale, you would go over A units on the real scale, B units on the imaginary scale, and there would be your complex number. But there's another way of representing that number, is there not? So instead of rectangular form, we also have polar form. Somebody tell me how to work my way through polar form.
Use R for this part of imaginary number.
Okay, good. So forgetting the math for a second, conceptually speaking, what I'm going to do is I'm going to draw a line here. And instead of representing this dot as being A plus JB, I'm going to say, okay, this dot is at the end of a stick. If I know how long that stick is and what the angle of the stick is, I get to the same, oops, tripped over myself. I get to the same dot, do I not? You do. Okay, so if I know how long that is, and if I know how long, what angle that is, I should be able to get to the same complex number. That's called polar form. Okay, so if I'm going to write this in polar form, what is my R? Can I write R in terms of A and B? Right, so according to Pythagorean theorem, R should be square root of A squared plus B squared. And my phase angle should be what? Arctan of B over A. This is all stuff you should have seen before, right? So, so how do you usually write that? Like, how do I actually write that complex number with R and theta? Do you do e to the j theta? You haven't done that yet. We're going to do it shortly. I don't know. I'm asking. I don't know how they represent it in your math class. You could tell me. I'm asking. Like, it's just a sincere question.
Final answer?
Yeah, like, forget the actual number, but like if I told you you have a polar number with R angle theta. Okay. Perfect. So that's good. So you've seen the notation. Cool. And how do we go the other way? If I had R and theta and I wanted to give you A and B, how would you say, what's A equal to in terms of R and theta? Rats, which one's which? Oh, yeah. R cos theta, and B is R sine theta. Good. There's your complex numbers. And we're out of time. So when we come back on Wednesday, accepting the possibility of a quiz, what we're going to do is we're going to learn a new way of expressing complex numbers that's not our angle theta. We're going to learn like a new method of expressing it in terms of complex numbers. So we're going to learn e to the j, m e to the j theta. Okay, thank you. Come again soon.